is Mathematics in the Modern World. Today we will talk about mathematics in nature. What do we expect to do in this chapter? In this chapter, we will learn to discover how mathematical patterns appear in nature. So, where can we see mathematical patterns? Second, we'll see or illustrate the Fibonacci sequence and the golden ratio. So what's the Fibonacci sequence and golden ratio? We'll learn about that in this chapter. Third, you will create an artwork using mathematics and geometrical patterns. So, exciting! You'll make your own artwork. And lastly, we'll learn to appreciate the artistry of mathematical patterns. All right, let's start this chapter with an exploration or a brain teaser. Look at these three pictures. What can you see? Do you see any pattern or similarity between the three pictures? Okay, you can pause this video and then check carefully. What patterns do you see? All right. I think you've thought about it well. Did you know that these patterns are actually based on mathematics? And let's find out how mathematical patterns appear in real life. Basically, mathematics focuses on patterns. And these patterns, to learn more about them, we will study sequences. Sequences are a list of things, like numbers, that follow a particular pattern. It can be infinite or finite. Well, let's break this down. It says a list of things. So it says things. It can be numbers, but it can also be letters. A, B, C, D, E, F, G. Okay? It can be numbers, it can be pictures, or even objects, or people. So sequences are a list of things. But for it to be a sequence, it should follow a particular pattern. So it can't just be 6, 13, 100, -5. It should follow a particular pattern. And then these sequences can be infinite or finite. When we say infinite, that means it goes on forever. Right? So there's forever in mathematics because there are infinite sequences, or they can be finite, meaning it ends somewhere. There is a limited number of terms in the sequence. Let's look at this sample sequence. You can see this is a list of numbers. 3, 5, 7, 9. And then you can see a ... We call that an ellipsis. 3 dots mean that the sequence goes on forever, or if it's infinite. If there are no ellipses, then that means the sequence ends somewhere and it is finite. We call the items in the sequence terms. So 3 is the first term, 5 is the second term, 7 is the third term, and 9 is the fourth term, and so on. Aside from term, we can also say element or member. They mean the same thing. How about these series of pictures? Can we call this a sequence? What do you think? Is it a list of things? Does it follow a particular pattern? All right, so there's your answer. It is a sequence because it is a list of things. These are pictures, and they follow a particular pattern. What's that pattern? It's an object falling into a glass of water. Okay. Now there are different types of sequences. The main ones are, first, the arithmetic sequence. When we say arithmetic sequence, it means the next term is gotten by adding or subtracting the same number to the terms. For example, let's see these two. Okay. In example 1, we have 3, 7, 11, 15, 19. Okay, I'm going to give you a minute to think. What do you think is the pattern here? Alright, so if you've guessed, it's adding 4. Yes, it is. So it's plus 4, plus 4, plus 4, plus 4. And since there's ellipsis, it means it goes on forever. It's an infinite sequence. How about example 2? What do you think is the pattern here? Look at it carefully. Think. Yes, we subtract and the numbers are decreasing. So it means subtraction. They're decreasing by 5, meaning we are subtracting 5 for every term. The pattern is minus 5, minus 5, minus 5, and so on. That's arithmetic sequence. The next type is what we call a geometric sequence. So when we say geometric sequence, it means it goes from one term to the next by multiplying or dividing the terms by a common ratio. Let's look at these examples. For example, here in example 3, we have the terms 3, 9, 27, 81. Okay, you can pause the video and try to see what the patterns are. Okay, so for example 3, yes, the pattern is times 3, times 3, times 3. How about in example 4? Okay, the pattern is divided by 2, divided by 2, divided by 2, and so on. So that's what geometric sequences are. Okay? We've learned about arithmetic sequence, where we either add or subtract. Then for geometric sequence, where we either multiply or divide a certain number. However, there are sequences that don't fall into those categories. They are not arithmetic sequences. Also, they are not geometric sequences. We call them other types of sequences. Let's look at example 5. You have to guess what are the patterns for these numbers. What's the pattern in this sequence? Okay, you can pause the video again, then think carefully what the pattern is. Did you get it? Right, so the pattern is minus 2 times 2, minus 2 times 2, minus 2 times 2, and so on. Right. As you can see, you are not adding or subtracting or strictly multiplying or dividing. It's a combination of the two. There's a subtraction and a multiplication. That means it is neither an arithmetic or neither a geometric sequence. How about example 6? Okay, what do you think is the pattern here? Okay, did you think hard? You can pause the video while you think. Right, so the answer is we have plus 2, plus 4, plus 6, plus 8, plus 10. Notice that, yes, they are all addition. So do we call this arithmetic sequence? No, because you are not adding the same number. You're adding different numbers. Although, yes, the operation is all addition. However, we are adding different numbers, so we can't call this an arithmetic sequence. That's why it's an other type of sequence. Okay, how about this one? This one is quite challenging. I think you'll have to really squeeze your brain a bit to find the pattern here. Okay, don't give up yet. You have to try. Remember, the most important thing is to try. Okay, so let's see. The pattern here is times 1 plus 1 times 2 plus 2 times 3 plus 3. Okay, was it fun? Did you get the patterns? Right, so now it's time for you to try it with your own patterns. You have to come up with your own sequence and then show it to your classmate and see if he or she can guess the pattern. This is an activity that we will do within the class, but you have to prepare this activity so that we can do it when we go to class. Alright, now that we've learned the basic types of sequences, we will learn a special type of sequence, which we will call the Fibonacci sequence. In the Fibonacci sequence, we get the next term by adding the two numbers below or before it. For example, it starts with 0 and 1. To get the next term, we add 0 and 1. So 0, 1, 0 plus 1, the next number is 1. 1 plus 1 equals 2. 2 plus 1, 3. 2 plus 3, 5. 3 plus 5, 8. 5 plus 8, what do you think is the next term? Right? 13. And 8 plus 13, 21. To get the next number, we add 13 and 21, we get 34, and so on. So the Fibonacci sequence is like that. You just add the previous two numbers to get the next one. So in short, we have 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and 89. How did these numbers become special? Okay, well, it all started with this guy, Leonardo di Fibonacci. He was doing a thought experiment one day, okay, and he was thinking, maybe he was bored during that time. He didn't have Mobile Legends to occupy his time, so he was bored thinking about problems. He was thinking about this problem of a rabbit population. So the problem goes like this. You start with newborn female and male rabbits, and then the rabbits reach maturity after 1 month. Okay? And then, when they mature, the mature female rabbit gets pregnant and gives birth to 2 rabbits, 1 male and 1 female every month. Assuming that the rabbits don't die, how many rabbits will there be after 1 year? Okay, so that's his problem, was thinking, how many rabbits will there be in 1 year, if that's the case? Okay, so he made this pattern. He started with 1 pair of baby rabbits. Okay, after 1 month, that 1 pair of baby rabbits became mature. Now, since they are mature after 1 month, they gave birth to a pair of baby rabbits, making it 2 pairs. So there are already 2 pairs of rabbits. Okay, the next month, the mature rabbits give birth again. Okay, and their previous baby rabbits became mature on month 3. So now there are 3 pairs of baby rabbits. On the 4th month, the original rabbits gave birth again. Their previous baby got matured, and the first babies, since they're already mature, also gave birth to new rabbits. Now we have 5 pairs of rabbits. And the same thing will happen on month 5, making it 8 pairs of rabbits. So now we have 1, 1, 2, 3, 5, 8 pairs. And those are Fibonacci numbers. Now, to answer the question, knowing the pattern, how many pairs of rabbits will there be on the 12th month? You have to prepare your answer. Write it down because we will discuss that in class. Okay, now these special numbers, 1, 1, 2, 3, 5, 8, 13, 21, these are called nature's numbering system. Why? Why is it called nature's numbers? What's so special about these numbers? They're called nature's numbering system because they appear so frequently in nature. Okay. If you take a pineapple, count the number of eyes in those pineapple. I dare you, go find a pineapple, then count the number of eyes. It's always going to be a Fibonacci number, either 5, 8, or 13. More often than not, those will be the numbers. Not 7, not 4, not 9, but 5, 8, 13. Those are the special numbers. Even in pine cones. As you can see, if you count the number of spikes in the pine cones, okay, you'll have, if you go this way, you'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But if you go the other way, you have 1, 2, 3, 4, 5, 6, 7, 8 spirals. And that's amazing, right? So why not just 10 and 11? Why not just 2 and 5? No, these are special numbers, okay? They are the two consecutive Fibonacci numbers. So 8 and then 13. It's always going to be those. And in this cactus, for example, how many spirals can you count? We have 1, 2, 3, 4, 5. It's a Fibonacci number again. Even in this sunflower, the number of spirals is also going to be a Fibonacci number. Even flowers follow the Fibonacci number. Okay. There are flowers, of course, that have 4 petals or so, but more often than not, it's gonna be 5 petals, 8 petals, 2, 3, 8, 13. Those are going to be Fibonacci numbers, and they appear so often, so frequently, that it's not just chance. It's not just random. No, these numbers are special because these are the numbers that appear so many times. Even in trees, okay, we can see the Fibonacci numbers in the branching of trees. You have 1, 2, 3, 5, 8, 13, 21, and so on. Another application of the Fibonacci numbers is what we call the Fibonacci spiral. So what we do is we start with a small 1 by 1 square, as you can see, the smallest square, the white square. Okay, and then we extend that to another 1 by 1 square. Okay, and then we extend that to a 2 by 2 square. So 1, 1, 2. The next square will be 3 by 3, 5 by 5, 8 by 8, 13 by 13, and 21 by 21, and so on. If we connect the corners of those squares, we form what we call the Fibonacci spiral. Now, what's special about this spiral, again, is that it appears so often in nature. In shells, in the shape of typhoons, in the shape of galaxies. This is the shape of nature. Even in art, artists use Fibonacci spiral to make their artwork beautiful. Even in buildings, as you can see, this is the Parthenon. This has been around for thousands of years. It's become an iconic building. It has stood the test of time because its design is classic. It's built beautifully because it used the Fibonacci spiral. Even in photography, you know what? Photographers are just wowed because for us amateur photographers, we're just used to making our pictures the focus on the center, right? But actually, professional photographers know that if you use this Fibonacci spiral, you'll just have stunning photos. They can't explain why, but they just find that if you use the Fibonacci spiral in layering or putting the layout for your photos, then it results in more natural looking, beautiful images. Even when you take selfies like this, so we're used to taking selfies like ching! But there are better ways. If you use the Fibonacci spiral, you can take awesome photos like this and this and this. Wow, right? So they can't explain it, but they can just sense that Fibonacci spirals, Fibonacci numbers, have something beautiful, have something natural about them. Right? And this video further explains Fibonacci numbers and how they appear in nature. Let's watch this.
Beautiful, isn't it? This painting was regarded in its day as one of the most accurate and elaborate studies of nature ever made. In my mind, an equation can be just as beautiful. Instead of paint and canvas, a mathematician uses numbers and equations to depict everything from the movement of atoms to the formation of galaxies. Mathematics can be used to view the world in a way that is as breathtaking as a Van Gogh, Monet or Renoir. The universe is literally painted with numbers. Have you ever counted the number of petals on a flower? Given the variety of different flowers in the garden, you might think that any number of petals was possible. But it turns out that many flowers like just 5 petals. And if it isn't 5, then they seem to favour other numbers, like 8, 13, 21. Perhaps you can see a connection between all of these numbers. You get each number by adding the 2 previous numbers together. So for example, 8 plus 13 gives you 21. These are called the Fibonacci numbers, and they're nature's favourite numbers. You find them all over the natural world. Take an apple, for example. Cut it in half, and you'll find 5 seeds at the centre of the apple. Count the number of spirals on a pine cone or on a pineapple, and you'll find 2 sequential Fibonacci numbers, say 8 and 13. Plant growth seems to obey mathematical rules, but it's not just flowers that like these remarkable numbers. Snails build their shells in very much the same way as the Fibonacci numbers are built. A baby snail starts off with a tiny shell, kind of 1-by-1 square house. As the snail outgrows its shell, it adds another room to the house. As it continues to grow, it adds more and more rooms. But since it hasn't got too much to go on, it uses the dimensions of the 2 previous rooms to build the next room in the house. Just like the Fibonacci numbers are built out of the 2 previous numbers in the sequence. The effect of this growth is to produce a beautiful but simple spiral. Just an example of how mathematical patterns are fundamental to nature.
Alright, so we've seen the importance of Fibonacci numbers in nature. Another application of those numbers is what we call the golden ratio. So we take 2 Fibonacci numbers, then divide the 2. So let's start with 2 and 3. So 3 divided by 2 is 1.5. Next, 5 divided by 3 is 1.66667. 8 divided by 5 is 1.6. 13 divided by 8 is 1.625. 21 divided by 13 is 1.615385. And if we continue dividing the Fibonacci numbers, the 2 consecutive Fibonacci numbers with each other, then what do you notice? What do you think happens to the numbers? They get closer and closer to 1.618304. And this result is what we call the golden ratio. The golden ratio is approximately equal to 1.618, and it's symbolized with the Greek letter phi, if you write it like that. This is also called the divine proportion or the golden mean. Why do we call it the divine proportion? Okay. Divine meaning godly, because they say that this is the number that God used to design the universe. Isn't that amazing? If God was a designer, he's probably a mathematician because he used numbers and patterns to create the world. Okay. This golden ratio results in natural-looking designs that are beautiful to look at. So for example, we see this in our body. The ratio of your hand, of your palm to your elbow will be 1:1.618. Same with the bones on your finger. It's 1:1.618, 1:1.618. So as you can see, our body is a manifestation of mathematics. Right. Another pattern that we can learn about is fractals. Okay. What are fractals? These are never-ending patterns formed by repeating the same simple shape. What's special about fractals is they have what we call self-similarity. So what self-similarity means is when you take a small part of the figure, it still looks the same as the entire shape. This is an example of a fractal. This triangle is called Sierpinski triangle. Okay. This is a fractal. As you can see, it's formed by repeating the same simple shapes. The simple shape is a triangle. And if you take the top part of this Sierpinski triangle, that small triangle at the top, it still looks like the whole triangle, right? So it's like if you zoom in to that small part of the triangle, it still looks like the whole triangle because it has the property of self-similarity. Okay, mind-blowing, right? Okay, so how do we create fractals? So we start with a simple shape. In this case, we use a triangle. And then we cut out a shape, an equilateral triangle in the middle of the figure, and that forms 3 triangles now. And then we repeat the same thing. For each of those 3 triangles, we divide them again into 3s by taking out the middle part. Okay. Now you have 9 triangles. Then we repeat that. Okay. We take out the middle part in each triangle. So now we have 27 triangles. 81. Okay, and this one 243. So as you can see, by repeating the same pattern, okay, we can form a fractal. These are other types of fractals. Okay, this one is a Coke snowflake. The third one, it used a square, and as you can see by the end, by repeating the same pattern, you'll end up with a fractal. Taking the small part of the figure looks like the whole thing. This is also an example of a fractal. As you can see, if you take a small branch of this figure, it looks like the whole thing. So this is a fractal because it has self-similarity. That's what you're looking for. Okay, so let's watch this video to explain more about fractals.
Today, let's have some fun with fractals. To start with, what are fractals? You've probably seen tons of fractals in nature, but you just did not know that they are fractals. One example is the fern in this image. Here's what a whole fern looks like. Now if we zoom into one leaf, look, it looks like the whole fern. Now let's zoom in even more, and look at this, it looks like the fern again. Some flowers are also fractal. At first sight, if we see this bunch of flowers, we can see that the bunch is made up of many small flowers. But actually, if you look closer, each of the small flowers is made up of even smaller portions. Just the same way that each portion makes up the small flowers, each small flower also makes up the whole bunch. So each of these smaller portions is in fact similar to each of the flowers and even to the bunch. This is also an example of a fractal pattern. Another fractal is a broccoli. And don't we all really love broccoli? As you can see, each of the heads of the broccoli resembles the vegetable as a whole. Now that you've seen these examples of fractals, you can probably spot your next fractal in nature by yourself. So what exactly are fractals? The word fractals comes from the Latin verb to break. Fractals are geometric patterns in which every smaller part of the structure is similar to the whole. How do we actually create a fractal? Let's first look at the Sierpinski triangle. It does look complicated, but we can create this in a few simple steps. Let's start with the black triangle. We can mark the center of each side of the triangle and connect the dots to make a new upside-down triangle. We then remove this triangle and are left with 3 smaller black triangles instead of 1. We take the centers of each of the 3 new triangles and again connect the dots to make 3 new upside-down triangles. Let's remove the upside-down triangle at the top. Look, we get 3 new triangles instead of the one at the top. We can now remove the one at the bottom left and finally the one at the bottom right. You'll notice that each time we remove an upside-down triangle, we get 3 new black triangles. So now we have a total of 9 even smaller black triangles. Let's see the triangles that we will remove in the next step. Now we can again take the top part of the big triangle and remove the upside-down triangles. We can continue on to the bottom left and then the bottom right. We already have 27 black triangles. If we keep going, we can make more and more black triangles at each step. And if we keep doing this forever, we'll have an infinite number of triangles, and all inside the one big triangle we started with. Let's have another example. This one is called the von Koch curve, named after the Swedish mathematician who came up with it. This time we start with a line and divide it into 3. We mark these points, then take out the middle. We take a line of equal length to the one we just removed and put it at an angle of 60 degrees. We can now connect the 2 lines, and this line happens to be equal in length to the line we just removed. So instead of one middle line, we have 2 new ones of the same length, making the curve longer. And notice that instead of 1 line segment, we now have 4 line segments. Now take each of these 4 new lines, divide them into 3, and take out the middle from each of them. Starting from the left, let's put in 2 new lines instead of the middles. You'll see that each of these lines is equal to the length of the ones we just removed, which means that the length of the curve increased again. We already have 16 line segments to work with. Let's take each of these and repeat the same steps. It's starting to look pretty. You can see that at every step, each time we add segments, we make the curve longer. If we keep repeating the steps, we make the curve longer and longer. Since we can keep repeating this forever, the length of the curve becomes infinite. This is what makes fractals special. Now we can move on to a more complicated and more beautiful structure, the Mandelbrot set. As we can see if we zoom in, we recognize the original structure again. If we zoom in again, we again recognize the same structure as the original image. This keeps happening as we zoom in again and again, and at each step, the image retains its beauty as well. In this video, we saw the beauty of fractals. We showed you how to recognize them in nature, and even how to create some simple fractals. We hope you had some fun with fractals.
Science! Out loud.
What do snowflakes and cell phones have in common? The answer is never-ending patterns called fractals. Let me draw a snowflake. I'll start with an equilateral triangle. Then I'll draw another equilateral triangle on the middle of each side. I'll pull out the middle and repeat the process, this time with 1, 2, 3, 4 times 3, which is 12 sides. If I do this over and over, the shape will look something like this. This is called a Koch snowflake, and it has a special property. No matter where I look or how much I zoom in, I will see the same pattern over and over. Never-ending patterns like this, that on any scale, on any level of zoom look roughly the same, are called fractals. We can actually draw a Koch snowflake on the computer by having it repeatedly graph a mathematical equation. Each time we add a triangle, one side of the Koch snowflake will turn into 4. After the first repetition, we'll get 3 times 4 to the first, or 12 sides. After the second repetition, we'll get 3 times 4 to the second, or 48 sides. After repetition number n, we'll have 3 times 4 to the n sides. If we do this an infinite number of times, we'll get infinitely many sides, so the perimeter of the Koch snowflake will be infinite. But the area of the Koch snowflake wouldn't be infinite. If I draw a circle with a finite area around the snowflake, it will fit completely inside no matter how many times we increase the number of sides. So the Koch fractal has an infinite perimeter, but a finite area. In the 1990s, a radio astronomer named Nathan Cohen used the fractal antenna to rethink wireless communications. At the time, Cohen's landlord wouldn't let him put a radio antenna on his roof, so Cohen decided to make a more compact, fractal-like radio antenna instead. But it didn't just hide the antenna from his landlord, it also seemed to work better than the regular ones. Regular antennas have to be cut for one type of signal, and they usually work best when their lengths are certain multiples of their signal's wavelength. So, FM radio antennas can only pick up FM radio stations, TV antennas can only pick up TV channels, and so on. But fractal antennas are different. As the fractal repeats itself more and more, the fractal antenna can pick up more and more signals, not just one. And because the perimeter of the Coke snowflake grows way faster than its area, the fractal antenna only takes up a quarter of the usual space. But Cohen didn't stop there. He designed a new antenna, this time using a fractal called the Menger sponge. The Menger sponge is kind of like a 3D version of the Coke snowflake. It has infinite surface area, but finite volume. The Menger sponge is sometimes used in cell phone antennas. It can receive all kinds of signals while taking up even less area than a Coke snowflake. Now, these antennas aren't perfect. They're smaller, but they're also very intricate, so they're harder and more expensive to make. And although fractal antennas can receive many different types of signals, they can't always receive each signal as well as an antenna that was cut for it. Cohen's invention was not the first application of fractals. Nature has been doing it forever, and not just with snowflakes. You can see fractals in river systems, lightning bolts, seashells, and even whole galaxies. So many natural systems previously thought off limits to mathematicians can now be explained in terms of fractals. And by applying nature's best practices, we can then solve real-world problems. Fractal research is changing fields such as biology. For example, MIT scientists discovered that chromatin is a fractal and that keeps DNA from getting tangled. Look around you! What beautiful patterns do you see?
Okay, so we've learned how useful fractals are. Fractals are actually used in antennas. Even the antenna in your cell phone uses a fractal. It has a lot of application in our daily life. Now, another type of pattern that is really interesting is what we call a tessellation. A tessellation is covering a flat surface with repeating geometric patterns and leaving no gaps. Okay. Again, you cover a flat surface with repeating geometric patterns and you leave no gaps. Okay. You can use simple shapes to complex figures, as you can see. So in this first picture, we can see that the person used a hexagon and triangles to create the repeating pattern, and it covered the whole surface, and there are no gaps, so this is a tessellation. For the first figure on the left, as you can see, they used squares and rectangles. For the upper right figure, they used pentagons, okay, and for the the lower right figure, they used hexagons, squares, and triangles. There are no circles there, mind you. No circles in the third figure. Okay? They just use hexagons, squares, and triangles. Okay? We also use tessellation in our everyday life, actually. For example, in the floor tiles that you see, those are tessellations because they cover the whole surface with a repeating pattern and leaving no gaps. Bricks on the road are also tessellation. So they use, in this case, they use the I shape. But you know, some artists go further. They don't just use simple shapes, they use complex shapes. For example, the one on the left uses birds. The one on the center uses goblins, okay? And the one on the right uses horses. These are amazing, right? Imagine making complex figures fit together. These are the works of M.C. Escher. And what's amazing about M.C. Escher is that he is an artist. He started by making wood carvings, making pictures on wood. We call that lithographs. However, he started to look at patterns and he became interested in mathematics. And when he added mathematics to his art, that is when he was able to create these interesting, amazing pieces. Okay, let's watch this video about M.C. Escher and his art.
The amazing thing about M.C. Escher is that he represents the perfect coming together of mathematics and art. These are two different worlds, but in his work they're brought together as one.
Born in the Netherlands in 1898, Maurits Cornelius Escher had no formal training in mathematics. He began his professional life as a graphic artist, making woodcuts and lithographs. As a young man, while visiting the Alhambra in Spain, he became fascinated by the geometric decoration of the Moorish tiles. It would be a defining moment for Escher as an artist. From then on, he would spend much of his life experimenting with an area of mathematics known as tessellation.
Tessellation is about regular patterns that divide the plane. That means that they split the plane up into lots of little tiles, and those tiles fit together perfectly. They don't overlap and they don't leave any gaps. It may seem that the premise of tiling a plane or surface with regular repeating units is a very simple idea, but it's absolutely fundamental to mathematics, and the reason is that it's about symmetry. What Escher does with this rather simple, stark, abstract mathematics is to add a human dimension and a fantastical dimension. He has little animals, little lizards, dragon-like creatures, funny little men, goblins and things like that, and he uses those for the shapes of his tiles. Escher's work really divides into two different periods. His early work is intuitive, no contact with mathematicians, his interest in tessellations, and that's about it. After he made contact with mathematicians, it becomes much deeper mathematically. You get all sorts of sophisticated structures. He's interested in dimension, in the shape of space, the topology of space, in infinity. Cosmologists think that our universe might actually be Escher-shaped. So some of Escher's work may have anticipated very deep features of modern cosmology.
Using only basic drawing tools, he created Circle Limit 3, an astonishingly accurate representation of space as it edges towards infinity. Nearly 40 years later, mathematicians confirmed that it was absolutely right to the last millimetre. Escher was excited by the work of mathematicians such as Roger Penrose, who created the impossible triangle. He was also fascinated by the unusual properties of the Mobius strip, an object that appears to have only one side.
What's fascinating about visual illusions to everybody is that they show us that we don't just perceive the world as it is. Our brains actually interpret what they perceive and make assumptions about what they're seeing. Escher's visual illusions give that part of our brain a real workout. What is this thing we're looking at? What am I seeing here?
Escher was inspired by this to create some of his most famous works, images that look convincing yet defy logic. The concepts of infinity, reflection, and the nature of visual perception were to intrigue Escher until his death in 1972, and his legacy lives on.
If you wander around university mathematics departments, you will find Escher pictures all over the place. You'll even find them in the textbooks, because they really do talk to mathematicians. And from today's perspective, I think mathematicians understand much more clearly what it was Escher was trying to do, to the extent we can actually write down formulas for some of the things that he does, and we can investigate what mathematical ideas lie behind them. Mathematicians know their subject's beautiful. Escher shows us that it's beautiful.
Alright, so that picture shows M.C. Escher. He looks like that, and he is an amazing artist because he was able to fuse mathematics and art. And now you will also create your own art. You will create your own tessellation. You're probably shocked. Like, what? Me? I'm going to create my own art, my own tessellation? What? No. But actually, it's very easy. I'm going to show you a video of how to do a simple tessellation that will really let your creative juices flow and will show how much artistic you can be. Okay, that was fun, right? So you can create tessellations by doing or by separating a bond paper into squares and then cutting out a figure. You can be creative. It can be a fish, it can be a bird, it can be a peacock, it can be SpongeBob SquarePants or anime or whatever you want. Okay? You can be creative and just let your ideas flow. These are our activities for this chapter. You'll have a video viewing of the short animation Donald Duck in Math Magic Land, and you have to answer the questions in your module. Okay, so this will be a homework for you. This activity will be an evaluation of your knowledge. Okay? It's about sequences. This one is making your own art using geometric patterns, specifically tessellations. And activity 1 is an activity where you will take pictures of the mathematical patterns that you see in nature around your home or school. Okay? You can see samples of these activities on the website so that you are guided on what to do. Right? See you in class!